So this is a waiting lines review. When I gave the lecture material is on Moodle. Now, given that the lecture happened just one day before the shutdown, and I noticed that not many students showed up for that class, so I'm just going to give a review, quick review, very important things about waiting lines. So pay close attention. So the first important thing is we have to understand what a single server is. So a single server is you have a waiting line, and that waiting line is served by one server. Here we have another waiting line, it's served by one server. So always one server per waiting line, one server per waiting line. We see this a lot in supermarkets where you have a lineup of people want to check out their items and there's an assistant to help with the checkout. In a multi-server problem, you have a waiting line that is serviced by more than one server. So more than one server. Here we have 3 servers, which makes this a multi-server problem. This is a multi-server problem because there's more than one server. The number of server will be called M, and in this case, M is equal to 3. If we only had 2 servers, then M would be equal to 2. So now I'm just going to talk about some very important symbols. We have LQ, which is the number of people waiting in line. So if we have this line and this is the server is here, this is the server. So the people waiting in line, that's LQ, the number of people waiting in line, or it could be products. Then LS is basically the number waiting and the number and plus the person being served. If it's more than one server, then plus all the people being served. So LS is the number of people in the system or product in the system. WQ is the average time a product or a customer spends waiting before being served. Waiting before being served. WS is how long does a customer or a product spend in the system as a whole. So this is waiting plus service. Okay. Another very important symbol is PO, which is the probability of 0 customers in the system. So PO is the probability of 0 customers or 0 product in the system. Now this PO has to do with the system, not the waiting line. So when we say the probability of, so if a question asks for the probability of 3 customers, we mean in the system, not in the waiting line. So if we have a question about a waiting line, if let's say if the question is asking what is the probability 3 people waiting, then you have to add the number of people being serviced to that for you to get the probability for the system. Now the probability for the system, they have very specific equations and they're system equations. They're not waiting line equations. Now there are more than very important. There is lambda and mu. Lambda is the arrival rate, how many people are arriving per hour, how many products are arriving per hour or per day. So this is lambda. Mu is how many products are being processed per hour or how many people are being processed per hour. It could be per day, it's per time period. Now there are more symbols, but these are basically the main symbols, the symbols you're going to be seeing a lot in the class. So we have 3 models that we're going to be seeing: multiple server, single server exponential, and single server with constant service rate. Now this last one here, this one right here, the last model, we only use it if the question says constant service rate. If the question doesn't say constant service rate, then we will always be using a single server model. This is for a single server. For multiple server, we only have one option. We'll use the multiple server exponential service rate model. Now, these are the basic relationships, and these are very important relationships we're going to use whether it's multi-server or single server. It doesn't matter. These are relationships between the different variables. So it's a relationship between ls, which is the number of people in the system, relationship to the number of people in the waiting line. Here is server utilization, which is lambda over m, which is the number of servers, over mu. So this is utilization. Server utilization is very important, and this is what mu, it's called rho. WQ, here's an equation for WQ. There's a WS, another WS. All these equations are going to be the equations we're going to be used to move from one variable to another. Now, in our cases, we're always going to calculate LQ first, and then from LQ we'll move to calculate LS, WQ, WS, and so on. So we have two different equations for WS on your formula sheet. You only have one equation, but since you will have your exam is going to be online, so you could have access to these two equations. This one might be faster in case you have .ls. If you don't have ls, then you could go quickly with WQ. Here are the equations for a single server model, LQ. And whenever we have a single server model, we're always going to calculate LQ here. So we're going to use this equation to calculate LQ. And then once we have this LQ, and if the question asks for LS, then we'll use the equations in the previous slide. PO is the probability of zero customer in the system. This is not number of customers, zero customers waiting in line in the system. PN is the number of customers in the system, not in the waiting line, in the system as a whole. So if we have 3 customers waiting and 1 customer being served, this would be a probability of 4 customers in the system. Okay, so sometimes a question might ask you what is the probability of 3 customers waiting in line. So what is the probability of this? Well, we can't say this is P3 because we have to include that 4th person being serviced, and this P will become 4. So even though the question is asking 3 people waiting, we have to think in terms of the system. So if we had 2 servers, then it would be 5, and so on. So you have to think in terms of the system. A single server constant service rate, this is only when the question tells you there's a constant service rate. Question doesn't tell you constant service rate, so you will always be using the first equation. And the equation is going to be a little bit different. These are the equations for multi-server models. Now, good news, you don't need to use this equation because you don't need to use this very long equation for the LQ because you have the table. So if you go on Moodle for the under the final examination material, you have a formula sheet and you have a sheet that gives you the LQ directly based on the number of servers and the ratio of lambda over mu. It's really quick, fast, so you could get it right away. So you don't have to go through this whole equation. WA has to do with PW. It's only used when you do PW. PW is the probability that customer has to wait. So any question asks for the probability the customer has to wait, then we're going to be using this WA and we're going to calculate it and put it in the denominator. And WQ, we already know how to calculate that. So because once we have LQ, we could calculate WQ. So the probability of customers in the system, we have to think about N and M. If N is less than M, if the number of customers is less than the number of servers, then we're going to be using this equation. If N is more than M, then we're going to be using this equation. This is the probability of that a customer will wait longer than some T value. So if a question asks you what is the probability that a customer will wait longer than 20 minutes, then this T is 20 minutes. And we just have to substitute that T. And we have to pay attention to the units. So T has to be in the same units as the lambda, and mu. So when we have multi-server, this table is going to make it really easy for us to find LQ and PO quickly. So the probability of 0 customers and LQ, we're going to find it really quickly. So what we need is the number of servers. So let's say if a question is telling you there's 4 servers. So you know that you're searching here in this column because it's m equal 4. And then we have to find out the ratio of lambda over mu. So we calculate lambda is going to be given in the question, mu is going to be given in the question. So we calculate that ratio. And if the ratio turns out to be, let's say, 0.7, then we go here where 0.7 is, and boom, we got to the PO and the LQ really, really quickly. Now this makes it much, much faster than using the equations. Equations will probably take you 10 minutes to calculate LQ and calculate PO and so on. It's a lengthy calculation. So right away you could get to LQ and PO using this table. This table is really great. So this is a good question to look at because it asks you so many things about waiting line. So you have a taxi company that has 7. So let's think about the question. There's 7 taxis. So we could think of the taxis as servers. So we have m equal to 7. We have lambda 6.6. Now 50 minutes, the service duration is 50 minutes. This is the duration. We have to convert it to a rate. So we take 1 over that service duration. And since our arrival rate is given in per hour, then our service rate should be given per hour, and we get 1.2 per hour. Now let's start with the first question. What's the probability of a customer being in the system? So we're looking at n equal 1, and this is so they're asking in the system, they're not asking the waiting line, so that really saves us the trouble of adding the number of servers. So it's basically we're looking for P1. So in this case, we have multi-server problem. So this is a multi-server because we have more than one server serving the same line, right? So we have to use one of the two equations. So in this case, n is less than m, which is 7. So we're going to use the top equation. And then from there on, we just go 1 over n factorial times lambda over mu to the power n times PO. Now PO is really easy to get because of that table. So it's really easy and quick to get. So now this is our table. So our table here is for m equals 4, 5, 6, 7. So we have m equal to 7. So this is where we want to be. And it is, we just have to calculate the ratio. So the ratio is going to be lambda over mu, which happens to be 6.6 divided by 1.2. So it's going to give us 5.5, and that's going to be right here. So if we go 5.5, we're going to get PO equals to 0.003. So really so remember we're using m equals 7. Remember that we have to pay attention to what m is equal to 2 on the vertical. Now this table really helps us because we could right away get PO and we could get also LQ really quickly too if we wanted. So now the probability of one customer being in the system is P1, and we plug in all the numbers. N is 1, and lambda is 6.6, mu is 1.2, and PO we just calculate PO, which is 0.003. So we should get probability of one customer being in the system is 0.0176. Now these numbers might be a little bit off because I calculated them using last year's table, which was a little bit different, but it shouldn't be that much different. So we get a probability of one customer equals to almost 1.8%. Now we're looking at the probability of 8 customers being in the system. So here 8 is greater than 7, so remember we have this condition, so n is no longer less than m, because our n now is 8, and 8 is no longer less than 7, so we have to go for the second equation right here. So again, we just plug in the numbers. So we just plug in all the numbers. And we should get the probability of 8 customers being in the system, 0.077%. Now this could be a little bit off because I'm using a different table. So the question now is asking us for the probability that an arrival has to wait. Now this is what PW is. The probability that a customer has to wait is PW. So the equation is PW is equal to WQ over WA. So we need to calculate both. So we'll start with WQ. This is the equation for WQ. And then WA, which is 1 over M times U minus lambda. So now we need to calculate WQ. So WQ, and to get WQ we need LQ, and the nice thing about this table is right away it's going to give us LQ, which is right here. So this is the M equals 7 column. So we get LQ equal to 1.6736. So now let's calculate WQ. We have LQ and we know what lambda is, 6.6, and we get 0.253 as our WQ, and we do the same thing for WA. We have the equation, should be in your formula sheet, and we just plug in the numbers. And we get 0.556 WA. So we know what WQA Q is, we know what WA is, then we just calculate PW, which is the probability that a customer will have to wait. We just plug in the numbers, and we should get PW equals to 0.455. So there's a 45% chance that an arrival will have to wait for service. So here they're telling us there's a waiting line for car repair, and there's 4 stations for the repair. So we have 4 stations to repair, 2, 3, and 4, and we have a waiting line. So this is the waiting line for cars, and then these are the cars serviced. They're telling us that there's 3 workers to staff each station. So at each station we have 3 workers. We have 3 workers in each workstation. Now, this could be a trick question because some of you might think, well, the number of servers, so what is the number of servers? You would think it's all the employees. So you multiply 3 by 4 and that's 12, but that's a mistake because these employees here are working at one station. So they're basically one server. Yes, there's 3 of them, but they're serving the same car, which means they're one server. So M, which is the number of servers in this case, is 4, and it is not 12. This is very important. It's a bit of a trick question. A lot of students might be tempted to say it's 12, but remember we have to think about how many customers are being, the number of customers at the server, not the number of servers in that station. So there's only one customer being served, even if it's served by 4 or 5 or 6, it still counts as one server. So here we have a line, waiting line. The server here is one baker assistant. This is at a bakery. The assistant has an average service time of 8 minutes, so 1 over Mu is 8 minutes. Now we see something new here. And the average time between arrivals, that's 1 over lambda. We didn't see that before, and that's 10 minutes. So just like we have service duration and we move from service duration to service rate, we can have the same thing when it comes to arrivals. So we can have time, average time between arrivals, and we could convert that to an arrival rate. The question asks us what is the average arrival time. So we don't need any service duration information. All we need is is the lambda information. So lambda would be just 1 over 10 minutes, which is going to give us 0.1 customers per minute. We could convert that to 6 customers per hour. If we want to have the answer in hours. Here they didn't specify that they want the answer in minutes or hour, so it doesn't matter which one. So you just calculate it per minute and you leave it at that. You don't calculate it per hour. If the question asks how many arrivals per hour, then you need to convert it to customers per hour. So we have a gas station, a waiting line at a gas station. The question is about a waiting line at a gas station. We know the arrival rate, so we know what lambda is, and we know what the service rate is. What is the average time car spends waiting? So basically we have these cars that are waiting for the pump to basically put in gasoline, and there's one car always being serviced. Once this car is gone, the next car moves. So this is a single server problem, obviously. So now we use the single server equations. Remember, we have two different types of single server equations, either constant time or non-constant time. Here we don't have the case of constant time. So nothing indicates in the question that is constant time. So we need to calculate WQ because they're asking us for the average time a car spends waiting. Some students might think this is WS. That's not correct. It's not WS. It's not the time a car spends in the system. This is how long a car spends waiting. Okay, so this is very clear that it is waiting time. This is in the queue. No service is included in this number. So to get WQ, we first need to get LQ, and the equation for LQ is lambda squared over mu minus lambda. So it's going to give us 10 squared over 12, 12 minus 10, so it's going to give us 100 over 24, which is equal to 4.167. This is LQ, and we use that LQ to calculate WQ. So WQ is LQ over lambda. We just calculated LQ, 4.167 over 10, which is going to give us 0.4167, and that's the answer. So 0.467 is the answer, and this is basically how in terms of hours. So an average car would spend 0.67 hours per hours in waiting. So it will spend 0.4167 hours waiting in this waiting line. So now we have a question about a manufacturing plant. There's this manufacturing plant, and they're adding one more repairman to an already another repairman that is already working there. So in total we have 2 repairmen. Now the rate at which the machines are broken is 3 per day. So the arrival of machines basically is 3. The rate of repair is 4, So the rate at which these each one of these repair person is fixing the machines is 4 per hour. And the question is asking how many machines would be waiting to be repaired. And that you should right away know that this is LQ. Now, since we have this very nice table, we could right away get to the answer. All we need to do, so this table right here makes it really easy for us. All we have to do is get the ratio of lambda to mu, which is 3/4, which is 0.75. So we look at 0.75, and the corresponding LQ is 0.1127. And again, M is equal to 2. So we're looking at this column. So M is equal to 2. So LQ right away, we know LQ is 0.1227. So there's 0.1227 machines waiting to be repaired at any time in this manufacturing plant. So this basically, I want to wrap up the review on waiting line. Waiting line questions could be tricky, so you have to pay attention. You have to pay attention, first of all, to understand, is it a multi-server problem or single server? So it's not enough to look at the question and find if the question says 4 servers, it doesn't mean it's multi-server. We have to draw it out. Maybe the 4 servers are serving the same station. So we've seen that example already. So you have 4 servers in one station serving the same waiting line. In that case, it would be a single server. So you have to visualize the problem. Try to draw the problem. It's going to help you out. Sometimes it is very obvious. Sometimes it's not so obvious. So remember, if multi-server, single server, there's 2 options, one constant time and one no constant, normal. So this is normal case and there's the constant time. There's only 3 models. Once you know the models, you know which set of equations to use. The other tricky part in these questions is to know the symbols. You have to know the symbols, know what they're asking. Are they asking for rho, which is their server utilization? Are they asking for PW? Are they asking for PO, WS, WQ? You have to see what the question is asking. Now, I highly recommend that you do all the tutorial problems, do all the practice problems. You're going to be seeing, do the practice quiz on waiting line, do as many questions as possible on waiting line. I've included in this review 4 additional questions you haven't seen before. You could actually also look at the lecture. I have more questions in the lecture, the waiting line lecture, not the video. So I wish you all the best and good luck.